Hello. In this video, we're going to figure out the equation of graphs, and we're going to look at domain-dependent cases. What I mean by that is we're going to look at cases where you have to specify the domain in order for the true equation of the graph to come out. The goals of this video is we want to demonstrate that you can modify the domain to suit the specific graph. Often people feel that they're working for the domain. Remember, the domain works for you. Unless someone tells you what the domain is in context to a question, you can specify a domain however you want to grab just a portion of that graph. The second thing I want to get out of this video is I really want to communicate the fact that finding the equation of a line is as simple as finding the equation of a circle. Often students will start learning about the equation of a circle and think it's this really new and challenging thing, but it can be reduced down to the same substitution process that you have for finding the equation of a line. Though again, I do want to stress the importance to understand where the equation of a circle comes from and how you can use it and derive it, because in doing so, it will give you greater access to more challenging problems. So just to start here, let's write down the equation of a line. So the equation of a line, and again, a good passive memorization technique is to write it down regularly. There's three forms for the equation of a line: y equals mx plus b, which is slope y-intercept form. The next form is x over a plus y over b equals 1. And this is the xy intercept form. The reason why I like to encourage students to remember the names is because the names tell you what pieces of information you need. And the third form, pen here, is standard form. And standard form is really not that useful for graphing, but it is good to be aware of it nonetheless. So now let's remind ourselves the equation of a circle. Remember, the equation of a circle is derived from the distance formula. So if we want a full circle, we say r squared is equal to x minus a squared plus y minus b squared, and that's going to give me my full circle. If I want the top half or the top semicircle, we actually take the square root and account for only the positive case. If I want the bottom half of the semicircle, again, I take the square root and I only account for the negative case. So where r is our radius and point AB is the center. So if we know the radius and the center, we can always find the equation of the circle. Part of the challenge in the question is figuring those out from what information is given. So let's do a couple questions together. So this first one here, we see it's a line, so we want to find the equation of this line, and I see I have 2 points. Now I can very quickly see here that I'm given the y-intercept, which is really nice. So I'm going to use y equals mx plus b form. So I could calculate the slope here. I could read it right off the graph, so I could count 1, 2 up, 1 across. So the slope is 2 over 1, rise over run. And I like to talk about these feel-good moments. I feel good about this because it's positive, and I see the slope has the slope is a positive slope. It's moving from left to right in an upward direction. And I can read directly off this graph that b is equal to -1. So therefore, the equation of this line is y equals to 2x minus 1. Now again, if for some reason the b wasn't as nice, what I could do here is I could say, well, y is equal to 2x plus b, and then I could substitute in any point on the graph. So let's substitute in a is 2, 3, and if I substitute a is 2, 3, what I'm going to get is 3 is equal to 2 times 2 plus b, and therefore, with a little bit of algebra, b is -1. Okay? So like I said, we always want to look and see if we can pull this information off the graph, but in reality, often it's not going to be nice, so you're going to have to do some calculations to figure that out. So let's scroll down here. So now what if I asked you for the equation of this? Well, it's a straight line, and in fact, if I imagine extending this, you'll see that this is actually the exact same straight line as last time. So what I could start with is I could say that the equation of this line is y equals 2x minus 1. Makes sense. But let's just scroll up here for a second. If you notice in this example, this line goes on forever. And I should indicate that with arrows, but I did this in GeoGebra, so it didn't put arrows on the end. But what I see here is that any x value can be plugged into this relationship and it gets a corresponding y value. If x is 4, y is somewhere up here. If x is 0, y is negative 1. So what we can say is x is an element of the real numbers. Now, I don't often write this, and let's just write this. X is an element of the real. We don't need to write this every time because it's just commonly accepted that if you give the equation of a line, x can be any real number. However, down here, this is a line segment. And we can see that even though I could extend this, and I could sub in values of x is 0, negative 5, negative 500, the graph is only defined from x is 2 to x is 3. So therefore, to give a little bit more description here to help the person see where this graph is defined, I'm going to state the domain. And to do this, I go from left to right. So I say 2 is less than or equal to x, which is less than or equal to 3. So now if I took this equation here and I gave this to someone to graph, they would know I'm only talking about the graph in this small little segment here. And so see that by using the domain, we can actually specify a small portion of the graph. So let's see some other cases here. All right, so let's find the equation of this circle. Well, really nicely, I have the center, and I can see on this that the radius here is 3. And again, this is great because I can read it off the graph, but if in the case where you couldn't, you could use the distance formula to find that radius, the distance between these 2 points. So therefore, this is a full circle, so I'm going to write it in this form. R squared is equal to x minus a squared plus y minus b squared, where r is the radius and a and b are the center. So I can say 3 squared is equal to x minus 2 squared plus y minus 3 squared. Now the temptation here is to square this and put 9 and to expand these sometimes. And try and get y equals. But again, relationships don't have to be written in the form y equals. We can write them in any form. Often we like them in y equals because that's how we first learn them. But again, we don't need to put this in the form y equals something. And this is what students will often give for this circle. Now, what I always stress with my students is that I tell them right from the start, let's give the domain of this. So if I take a look, I'm going to look for the leftmost x value here, and that's negative 1. So negative 1 is less than or equal to x, and then I look for the rightmost value of x, which is 5. So now I've communicated to the person reading this that this is the equation of the circle, but the only x's that make sense are negative 1 to 5. Remember that if I happen to substitute in something like 100 for x, I'm going to end up with the square root of a negative number, which means it doesn't make sense. And we have some other videos where we demonstrate that. So this little bit of information on the side is really helpful in communicating just added information to the user. Let's take a look at a couple more challenging cases. So here we have a quarter of a circle. Okay, so this is the center. So again, we can do the same processes with the line. If I imagine extending this, I'm going to get a semicircle in the top half. So we know the semicircle is r equals to the square root of x minus a squared plus y minus b squared. So in this case, r is 3. I can read that right off. So 3 is equal to the square root of x minus a, and a is 2 squared plus y minus 3 squared. And if I gave someone this equation right here, what's going to happen is they're going to graph this entire upper portion of the semicircle. But notice this graph is only defined from negative 1 to 2. So I'm going to state the domain. Negative 1 is less than or equal to x, which is less than or equal to 2. And now I've communicated a further piece of information for the user. Let's take a look at another one. So this one looks a little funny. Now, you would have to know that this is a circle in this case, and you could probably figure this out, given some other information. But I'm going to tell you that this is part of a circle, and the center is 2, 3. So in this case, this is actually the exact same circle as above, but all I've done is I've taken the point D and moved it to x equals 0. So again, when I write this out, I'm going to have the same equation. 3 is equal to the square root of x minus 2 squared plus y minus 3 squared. But now I'm going to restrict the domain so I only talk about this small segment of the circle. So negative 1 is less than or equal to x, which is less than or equal to 0. So now I've given the equation, but I've restricted the domain to tell the person using this that I'm only interested in this small little segment. So again, the big takeaway from this is that when you're actually finding the equation of lines or circles, you can actually give the domain that the circle or line is defined on, and by doing so, you can actually give small sections of it. This idea of using the domain to define sections of graphs are really useful, and it's something that's good just to learn now. And you always want to be thinking about is, what is the domain of this graph? Because if you are in grade 10 math, the grade 11 course in the Ontario curriculum is you start getting into functions. In functions, you explore all sorts of ideas around domain. And one of the things we really want to encourage students to do is when they see a function, is to right away think about what x values make sense. I hope this video helped.